Today we're going to continue on with our discussion that we started last week in learning about deep learning and neural networks. And so now we're actually going to talk about what a neural network is. What we've done so far is we've seen some of the motivation for these ideas that we're going to discuss, and then we've seen the basic building blocks. So last week we talked a lot about perceptrons, which are some sort of artificial neuron. Neural networks are what we get when we take perceptrons and join them together. So neural networks are networks of perceptrons. So artificial neurons. All right, so if the perceptron was at least in kind of an early attempt to construct some sort of artificial neuron, then one way to think about neural networks correspondingly. So if we're networking together artificial neurons, what we are hopefully getting then is some kind of artificial brain, right? So a neural network is an attempt to construct some sort of artificial, an artificial or computational mathematical brain, however you want to describe it. Okay. Now, as it turns out, they're not quite at that level, even like the more complicated ones. Of course, the human brain is an extremely complicated computational object in some sense. But modern takes on, say, artificial intelligence and so forth use a lot of these ideas, but are considerably much more complicated than anything we're going to discuss here. The computer programming is much more difficult, et cetera, et cetera. But some of the so neural networks at least were kind of an initial attempt to say, okay, how can we try to create some sort of computational analog, some artificial analog of a brain? They don't really do that exactly, but they're not quite, they're a long way from being there. But now modern techniques use a lot of the same ideas, and so as we'll see, neural networks and related concepts are useful for kind of what you might call higher level problems. Okay. So for instance, AI type problems like self-driving cars and so on rely a lot on neural network machine learning architecture. All right, so before we kind of get to some of that, talking about some more of these problems that we use them for, let's just talk about the basics of neural networks. So we'll start with the basic structure. And the basic structure of a neural network is what are called layers. So the essential idea here is to join together perceptrons both in parallel and in sequence. Okay. So with the neural network, there are three basic areas. One of which is what's called the input layer. So where does the information come in? There's a second level, and then I'm going to skip that just for a second. And then the third level is the output layer. Okay, so the word layer here isn't really doing a whole lot. The idea is that at the beginning, the inputs all come in at the same place, and then at the end, the output or outputs go out. Okay. But what really makes a neural network is the second level here, what are called the hidden layer or layers. Okay. So the idea is between the inputs coming in and the outputs going out, things are happening. And what they're happening at what are called the hidden layers. And the one reason for the name hidden layer or hidden is we don't really see, we see what goes in, that's our input, we know what that is. And we see what goes out, those are the outputs. But we don't actually necessarily see what's going on at the hidden layer. Okay, so here then is what a basic neural network looks like. So we have an input layer where the different inputs come in. And notice then, so those inputs are then all sent out to the hidden layer. And so now think about any one of the nodes, the circles at the hidden layer. Think about that as like a perceptron before. Okay. So notice there's a bunch of inputs coming in, these arrows, and yes, the arrows can be weighted, as we'll see, just like our perceptron. So the top one here, right? There's 4 inputs going in. The idea is that the inputs just come into the input nodes and then get sent out to all the nodes at the next hidden layer. Okay, at the hidden layer here. And then at that input node, the information is processed with a net input, and then it's sent out via an output arrow, essentially, an activation function to the next level. In this case, the output layer. Okay. So the inputs come in, they're sent to all the nodes at the hidden layer. The nodes process those inputs in various ways corresponding to weights, and then they send information through the activation function to the output layer. At the output layer, all of those are processed, and then it generates an output. F of x here is simply a symbol trying to denote the output of the algorithm. Okay. All right, so that's what a very basic neural network looks like. With you have some inputs, you have some nodes at the hidden layer, and then you have an output layer. So when we have more than one hidden layer, so lots, and in this case, just more than is really just going to mean more than one by definition, but typically we do in kind of more advanced applications, you will have many of these. So lots of hidden layers produce what we call deep neural networks. So formally then, a deep neural network is going to be one which has more than one hidden layer. Okay, that's all we're going to require for the definition. We are frequently going to abbreviate this by DNN. Okay, so we're often write DNN, that means deep neural network. So DNNs. Okay. All right, so the whole idea then is that with a deep neural network, rather than the sort of simple one we just showed, there's multiple hidden layers. So hidden layers are passing information. They're producing outputs and then passing it to the other hidden layers as inputs. So here then is kind of what a kind of a generic deep neural network would look like. Okay. So what we have is we have the input layer. So remember, so x1 through xp, these are our features. And they are fed and then they are sent to the first hidden layer, which we're calling here L2. Okay. Now, the notation at the bottom, W1, the whole idea here is that there's weights on all of these arrows, right? So that's just a vector of weights corresponding to all the inputs and all the places they can be sent. Okay, so just simplifying the notation a bit. Otherwise, we obviously this would get really messy if we tried to label every single arrow in the picture. Okay, so the inputs are essentially they're initialized at the hidden layer or at the input layer L1, and then they're sent to the hidden layer L2 as the inputs for that hidden layer. At every one of the nodes at the hidden layer L2, that information is processed into a net input, and then those are outputted to hidden layer L3. They're sent through activation functions, and then they're also subject to weights. Okay, so they both take they're simultaneously an output for the hidden layer L2 and then an input for the hidden layer L3. And then the process repeats, right? So they all enter L3 according to the weight scheme W2 in this picture. They're processed there, and then they're all sent out to hidden layer L4 with the weight W, it's like the W superscript 3 here. And then finally, at the hidden layer L4, information is processed and it's sent out weighted and through the activation functions to hidden layer L5. Or sorry, output layer L5. Here, the information is processed and it generates outputs. Okay. So what's the notation here? Y0, Y1 through Y9. That corresponds to the example we're going to talk about, which is the MNIST example we've seen before. And so the idea is that you have these different outright. It's a multinomial classification problem. So you have sort of different outputs, say output probabilities for the digits 0 through 9. That's the what the notation is trying to imply here. All right, so you see then there's lots of information processing going on, lots of information being passed from one level to the next and being subjected to the weights. And then I've mentioned the activation functions. We don't see them here. We're going to talk more about that on Thursday, but that's going on as well. So there's a lot going on here in this picture. All right, so let's talk a little bit about this. So the idea behind neural networks is they can, in some sense, find information in an automated way without you having to kind of guide them necessarily. Okay. So the hidden layers in deep neural networks, one way to describe what they do, and we'll go into more detail on this over the next kind of few days, is they allow what we might call auto-identification of useful features. And what we mean by auto-identification is you don't necessarily have to explicitly define the features. So in other words, in some sense, the neural network can almost come up with features like of the data, right? It can kind of discover them on its own without you having to tell them what they actually are. Okay, so so let's compare and contrast. Okay. Let's compare and contrast with a simple machine learning algorithm, like multiple linear regression. Okay. So the features need to be explicitly defined first. So what do we mean by that? Okay, well, let's talk about an example. So let's go back to the MNIST digit recognition problem. Okay, just as a reminder of what it is we're talking about here. So MNIST is this big, this data set with all kinds of digits. So here are some of so it's handwriting samples of digits. And the idea is to train an algorithm to associate certain writing with that digit and be able to predict what digit somebody has written down with a high level accuracy. Okay. So what MNIST consists of, as we've discussed, is essentially for each digit, each handwritten digit, each piece of writing sample, it's like a big matrix of pixel values, basically indicating darkness of the pixels, that allows you to try and essentially then recreate what the image is. It's like you can translate it back into essentially writing. Okay. Now, what we talked about before was you could do something like a KNN, K-nearest neighbors algorithm, to simply have it try and group together the pieces of writing. In other words, the pixel patterns, so to speak, that are the most similar to one another. And then if you feed it new information, it's going to say, okay, well, what's it most similar to? And it's going to make that prediction. So it's not really actually, in some sense, picking out any of the qualitative features of the data, like say thickness and angles and so on. It's simply just looking at, okay, here's a grid of numbers that correspond to pixel values. What ones do I have that are the most similar to that? Okay. So I'll go back and let's talk about that a bit. So an algorithm like KNN doesn't really try at all to identify features. It just looks for pattern similarity. On the other hand, hidden layers in a deep neural network can identify and learn about angles, thickness, circles, completeness, etc. Now, what we mean by this is, now, of course, the deep neural network is not going to figure out the word circle. It's not doing that. But what it's going to do is it's going to be essentially what it can do. The hidden layers can do is identify that there is a characteristic in the data that we would describe in words as circles, and it can figure that out. It can learn that, like what that essentially looks like. Okay, and same thing like thickness and so on. Okay. KNN isn't really doing that at all. It's not looking for like what is a circle. It's just what it's gonna do is it's gonna realize, okay, all the zeros are pretty similar to one another in terms of their pixel pattern, or at least more similar to one another than they are to ones, right? So that's what's gonna happen. Whereas a deep neural network can kind of can figure this stuff out without actually having to be told to look for circles. It can learn that that's an important characteristic, a feature of the data. Okay. Now, how would we do this with, say, like an algorithm like linear regression? So a parametric algorithm. Okay. How could we do this? So remember what we mean by a parametric algorithm is one where we have to we have explicit, essentially, variables for the features multiplied by scalars. So in other words, an explicit function form for the how the algorithm works. So like multiple linear regression. Okay, so let's say we've got, let's just write down a multiple linear regression model, right? Y hat equals beta 0 plus beta 1 x1, where x1 is some feature, plus dot 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 plus beta p xp. Okay, so let's say that like x1, this is thickness, right? We're going to say, okay, we're going to have one of our features is going to be thickness. Let's say that xp here at the end, let's say this is completeness. Okay. All right, but then if it's going to be a variable in the regression, we need some way to kind of measure it, right, or quantify it. So how to measure or encode if it's a categorical variable, quantify, etc. Right? So we need to tell it beforehand, okay, if we're going to have a parametric algorithm like this, how to work with the different features of it. Right? Okay. So going back to the KNN example, so in chapter 8, if you want to go, we didn't cover chapter 8, but we mentioned a KNN a few times. So an MNIST prediction model is trained on similarity to data points. In this case, data points being pixel density grids. And as mentioned above, it's not really just looking for similarity. It's not actually, say, identifying anything about the features, any kind of features of the data. It's just looking for, okay, if given it fed in the data point, what other data points is it most similar to? And if you feed it something and it says, okay, this is most similar to the zeros, it's going to classify, it's going to identify it or predict it as a zero. So what's going on then? This is an example of what we describe as a shallow model. Okay. And I don't mean shallow in the decision tree sense. So not to be confused. With a shallow decision tree. Random forest, which of course tends to use overfit deep decision trees, is also a shallow model. Okay. In fact, everything we've described so far, everything we've talked about, anything else you've probably seen elsewhere, would be what we call a shallow model. Okay. So what we mean by this is we're only looking at one representation of the feature space, right? So we have our data set and we have the features in the data set, the columns. And so in this case, then features is probably just going to be basically, okay, what row and what column are we in, say, the grid, right? And then in that row and column, in other words, given a position, it's going to give us a pixel density value for that position, right? Okay. So I already mentioned RF is also a shallow model, so let me just kind of point out. So the same is true of multiple linear regression, basic decision trees, whether they're deep or not. Oh, clean that up a bit. Random forests, gradient boosting machines, etc. And basically everything we've talked about, everything you might have seen elsewhere, they are all shallow. Same thing with other like clustering algorithms, PCA, blah, blah, blah. In the sense that they consider only one or a few representations of the features.
Sorry to interrupt, Julian. I'm just curious which chapter note will this be? Like I just want to keep the notes open. I'm not trying not like the old notes.
We're in chapter 13. It's just
chapter 13. Yeah, is it part 3 or part 2?
I guess this should be like, well, this would be part 3 when I actually post the notes, because the third lecture.
Oh, okay, yeah, I found it.
It's not like necessarily counting the sections in the textbook though.
Yeah, that's okay.
Yeah, and so there's the description. The textbook in this chapter is way kind of short. It just doesn't have enough depth. So I'm talking about a lot of things that are discussed there, but like I'm adding a lot of extra detail.
Like the notes have so much extra fine points which need to be considered in real world. Like, yeah, that's true.
the textbook is not an especially deep discussion, but it's in that sense it's good because it provides a good outline for each topic, and it's not hard to read a chapter in say an hour or two. That's yeah. There's especially on this chapter, I've added a lot of extra details and context, examples, and so on.
Yeah, that's true.
So the basic point we're saying here about when I'm saying here about why are these shallow models? They basically take the features, in other words, the data set and the columns in the data. They take them as is and work them. They don't really they don't do a lot of transformations to them, changing them in some sense. Okay. So deep neural networks, on the other hand, as the name suggests, are what we might think of as deep models. The whole idea behind deep learning is that we can go further than these shallow models allow. Okay, what do we mean? So they can learn. And how do they learn? Well, that's something we'll get to later. Many different representations of the features. Okay. So like with MNIST, right, as an example, the deep neural network can learn representations of the features in the sense that it can start to associate particular patterns of pixels with circles, with angles, and so on. Even if it doesn't know what the words are, it recognizes, say, a right angle eventually, like and so forth. And that's what we mean by kind of representations. It can auto in the sense of it learns on its own in the background. You're not having to telling it anything, and it figures this stuff out. It figures out in some sense what a right angle means computationally, even if it doesn't know the term. Okay, and that's a representation of the pixel set of the features we're given, and so forth. So as a result, deep neural networks are well suited to these complex problems. Like MNIST, so like being able to recognize digits from handwriting. Okay. So what do you mean by complex problems? Problems which are often nonlinear, high dimensional, involving large data sets, where feature engineering, in other words, what we've kind of been talking about here, being able to essentially create features in the data, so where feature engineering is important, but hard to do manually. Manually meaning, like we were talking, how would you encode what a circle looks like in the pixel, in say a pixel grid, in a way that you could use it in a linear regression, right? You'd have to kind of describe, you'd have to basically manually create that feature and encode it. Okay, so this is the sort of problem where deep neural networks really shine. So things involving sort of, like kind of recognition in spatial dimensions is another one, right? So like any kind of work on self-driving cars, the coding architecture is going to often be some sort of neural network type architecture because of the fact that they work well for the kind of problems like a self-driving car needs to deal with, which is sort of recognition of shapes, of spatial dimensions and boundaries, identifying colors, all kinds of other things like that.
How scary is it that we don't know how exactly this algorithm works, and like they are sort of black box, and we make them do such complicated tasks?
I mean, yeah, that's a bit of a rabbit hole that I don't want to go down right now. But I mean, I don't know. It's the black box. I mean, we'll talk. I mean, we'll get into that a little later, I guess. But yeah, neural networks are extremely black box, like even more so than some of the other algorithms we talked about. We talked about black box kind of algorithms as a generic kind of issue on like the first day, but yeah, it's definitely something to keep in mind when it comes to actually trying to apply deep neural networks to real life problems. Is that the black box nature of them can make it hard to necessarily say what they're doing. So worth keeping that in mind. Now, deep neural networks can also handle what we might think of more as like traditional machine learning problems. Like the Ames housing example, right? So one where we have a fairly kind of standard type data set and kind of an obvious target variable, and you're just trying to make predictions on the target. Okay. But often rather, for these kinds of problems, so what do I mean kinds of problems? Like, so smaller, what we call them, the smaller values of n and p. I won't try to define what I mean by smaller right now, but something like in the context of neural networks, something like the Ames housing data set is very small. Okay. Where you have just kind of values in the thousands or hundreds and so on. Neural networks tend to shine with extremely large data sets. Okay. For these kinds of problems, like shallow algorithms are usually more computationally efficient. This will become more clear kind of next week when we talk about training and tuning neural networks and what's going on. We see that they are computationally quite complex and perform as well or better. Neural networks, among other things, can have a tendency to overfit to small data sets where they just learn sort of too much. It's easy to have that happen. So with most of the kinds of problems that we would encounter, say in a class like this, or in like, so for instance, in the DSci401 class, I kind of suggested to my students that they'd probably not bother looking at a neural network with the sort of data set that we were considering, because there's simply not enough features in it for a neural network really to be likely to be a useful approach. But maybe not. It's but certainly then it'll also be computationally. It would take a long time to train. Okay, so we'll talk briefly here, just as a little introduction to just what are some of the more kind of advanced areas here. Let's talk about deep neural network architectures. I'm not going to say very much here. The whole point is what we're going to do in this class. In other words, over the next a week and a half or so, or 2 weeks, is talk about the simplest form of deep neural network architecture, and that's more than enough. So there are many different. When we say architecture, we mean the sort of overall network structure. There are many different architectures for deep neural networks. So here are a few. All right, well, we'll start with the one that we're gonna talk about, which are what are called feed-forward deep neural networks, okay, aka multi-layer perceptrons. And so then, as that name suggests, this is what we get when we simply network together perceptrons, in the way we've described perceptrons already. Okay, so information moves in only a forward direction through the network. Okay. So information passes from perceptrons to other perceptrons in a forward direction. And so this is essentially what we already looked at earlier, but let's take a kind of another look. So this is just a basic example of what we've talked about before, what a perceptron network roughly looks like. Something like this. So if we were doing a regression problem, this would be a basic feed-forward deep neural network, in other words, a multi-layer perceptron. So we have the inputs come in, they go to a first hidden layer of perceptrons. Those perceptrons process the information, send them to a second hidden layer of perceptrons. Those perceptrons process the information, send them to the output layer, which generates an output. So very similar to what the examples we looked at last week, just now with multiple perceptrons joined together in multiple layers. The information is all moving in the same way, as we've seen. Okay, so a richer picture would be the other one we looked at earlier. So this picture of it, the picture we saw already of a deep neural network. Let me bring it back up. That's also this is a feed-forward deep neural network, okay, aka a multi-layer perceptron. The one way to tell, the easiest way to see, is that if you look at, although it's a little hard maybe perhaps to see them because they're small, but if you look at all the arrowheads, they're all going in the same direction. Arrows move from left to right with the arrowhead, in other words, the kind of end of the arrow on the right. So information here is starting at the input layer L1, passing to L2, then to L3, then to L4, and finally the output layer L5. And it never goes backwards. Somewhere it already been. All right. Well, so that is in some sense then the most basic type of deep neural network. It's got the simplest behavior, and that's what we're going to talk about as we go forward. No pun intended. But there are many other types as well. The most basic kind of improvement, or perhaps not improvement, but a thing you can do to make this more complicated is to have information go in different directions. And then we get what are called feedback neural networks, feedback deep neural networks, or another name for these is recurrent neural networks. So RNNs. Okay, so as the name suggests, information can be passed back from hidden layers to previous hidden layers. Okay, so it flows both forwards and backwards. Okay, so here then is what that would look like, and this is certainly much more kind of typical in some sense of how an actual human brain would work, right? We don't just understanding the brain is very complicated, but essentially we do know that information, say like image processing taking place in the visual cortexes, information is passed back and forth between them. It doesn't just go from V1 to V2 to V3 to V4 and so on, but information from the later visual cortexes gets passed back to the earlier ones. So in some sense, they can improve, knowing more information, they can improve on their previous kind of outputs in some sense. So everything you kind of keep learning in some, and that's exactly, of course, how you would expect a brain to work. Okay, so here's just a basic example of a recurrent network. You have your input layer, your hidden layers, and your output layer, and then at the input layers, or sorry, at the hidden layers, information can pass back from one hidden layer to a previous one, and in lots of different ways as well. Okay, so in this case, that single arrow going backwards turns this into a recurrent network. And then the idea is that the previous hidden layers get to relearn from information that they've already seen, but now they can learn it better because the next hidden layer is giving them additional information. Okay, the next several I'm not going to say much about, and we're not going to have any images, but next kind that are well known, or at least are popular, were called convolutional neural networks. So CNNs sometimes, not to be confused with the news channel. And so the basic idea here, as this name suggests, if you know what a convolution transformation is, they employ these. Okay. So these employ mathematical transformations called convolutions that are particularly useful for problems such as image and sound processing. Convolutions, I'm not going to get into this, but they will, in some sense, generically what they do is they transform information, so data from one kind of spatial representation to another. In particular, they are very helpful for interpolating between discrete and continuous spaces. So it's discrete data, continuous data. And this is what happens a lot with image processing, such as X-rays, and then sound processing. The idea behind sound processing is you take, in some sense, a continuous sound wave and you break it up into discrete units, discrete little packets. And this is done through something called the Fourier transform. At least this is one of the most common ways of doing it. And the Fourier transform can effectively do this. It can transform from a continuous space using sine and cosine waves to a discrete space, and then turns them into summations. All right, another kind, or what are called, I'm just going to give the name here, long-term, short-term memory networks. LTSMs. All right, so I'm not going to write anything about these, but essentially the idea is, as the name suggests, the network has both long-term memory and short-term memory. So in other words, information that it's learning, some of it's held on for longer, and then some of it's discarded more quickly. And the idea, again, is to mimic how the brain has both long-term memory and short-term memory. That's the motivation behind it. They're what are called autoencoders. I'm not going to say anything about these, but they are a topic in the textbook in another chapter. Oops. Hot field networks. So HNs, AKA, these have kind of a fun name, spaghetti neural networks. Why are they called that? Everything is connected to everything else. So they have a sort of maximum number of connections. And then finally, kind of a very modern topic that's still in some sense in its kind of infancy in the stage where people are trying to work out what it should be. What are called quantum neural networks. And so the idea here then is, and this is again quite at a relatively theoretical stage still, replace sort of ordinary information with quantum information, what are called qubits. And there are a lot of technicalities that need to be resolved if you want to do that. Among other things, quantum information has linear assumptions because you're using linear operators. But the activation functions that we want in neural networks, as we'll see, are often nonlinear. So that creates an issue, among others. There's even like debate as to what do we mean in this case by quantum. And one thing is to use qubits, so quantum information instead of ordinary information. Another is to use quantum computing with more classical architecture, or both. And so this is just kind of a very, in some sense, still a bit of a speculative area, but it's sort of at like the frontier of kind of what the modern research on the subject is. At some point, it's possible that major breakthroughs will happen here and just, I mean, create, yeah, no pun intended, quantum leaps forward in computing and in information processing and AI and so on. But we don't know. That's yeah, a bit far outside of my depth, but there's all kinds of puns when you talk about this stuff, right? Outside my depth, it's like, yeah. Anyway, we'll move on. But if you are interested, Wikipedia is not a bad place to start, just to read about what kind of these entail. I do mathematics that's very much related to quantum stuff, so I find this interesting. But there's definitely a lot there to the sauce to even just be resolved to get the basic architecture and so on. All right, so back to more grounded reality. Let's talk about feed-forward neural networks. Okay. So there are two main aspects to network architecture. They are layers and nodes, and activation functions. The activation functions are where a lot of the richness comes from, a lot of the flexibility of neural networks to do various things you want them to do. And so what we're going to do is we'll spend basically all of Thursday discussing activation functions, the different kind of choices that can be made, and how they affect the behavior of the network, and why you might want certain more complicated activation functions over simpler ones. So what we'll do for the remainder of today's class is just talk about layers and nodes, because there's not as much to say here. And then we'll deal with activation functions on Thursday. Okay, so as we've already seen, we have the following basic structure for the layers. We have an input layer. These are the original features. So in other words, the features of the data as it's presented to us. The hidden layers. And so then the way to think about the hidden layers, these are the learning layers. This is where the network is learning about the data and the features and learning new features that it can formulate. And then finally, there's the output layer. Okay, so the type of output, signal intensity, etc. So various things go in there. Okay, so there's not a whole lot to say about the input layer or the output layer, although there's at least the output layer a little bit, just essentially what type of output we want and so on. Okay, so the input layer, I'll just mention this very quickly. You have one node for each feature in the original data. And we've already seen that in the pictures, right? So there was for each data point, or each feature x1 through say xp, there was a node. And so that's simply where the information goes in, and then it gets sent out to all the hidden layers. It's not much to say there. Hidden layers, plenty to say. Okay. So the number of hidden layers and the number of nodes at each hidden layer are hyperparameters of the deep neural network and can be tuned. And this is something we'll talk about next week. So the idea is you can initialize a certain number of them, but then you can tune the number of them as well in both cases, the number of hidden layers and the number of nodes at each hidden layer, and that can vary from one hidden layer to the next. Okay, so we're not going to say too much at the moment. We'll talk more about the specifics when we do get to talking about tuning them. But what are some general observations we can make? Okay, so generally, more hidden layers the better. Okay. So perhaps not too surprisingly, deeper is better for deep neural networks. More hidden layers gives essentially more opportunity to learn, more ability for the network to create new transformations of the features and new representations. Okay. The number of nodes will depend on the number of features, among other things. And obviously, among other things is not a very specific statement at the moment, but the basic point is here that we're making some very general kind of comments, but there's also, of course, overfitting is always a problem and we need to think about. And so then we need, if we are tuning these, to think about whether or not we're overfitting on the data, etc. Okay. But basically, the whole point is that so number of nodes less than or equal to number of features is typical, but certainly not required. So these are more just sort of guidelines and observations than anything else. Okay. Now, you might say, well, why not just keep adding, go deeper and deeper, more hidden layers, more and more nodes? Well, as the number of hidden layers and or nodes at each hidden layer increases, so does the computational complexity. And as we'll see when we discuss training and tuning, this for deep neural networks, computational complexity explodes very quickly. And so this is always a big consideration. Okay, so runtime considerations for deep neural networks for training them and tuning them are something that we really have to keep in mind. Neural networks as kind of as a machine learning architecture got more popular as computational power available sort of to normal people increased, right? And once upon a time, only say big universities and research labs had supercomputers and so on. But now, the advent of modern GPUs and so forth, this becomes a lot easier. You can train a neural network if you have an NVIDIA GeForce 3080 graphics card or something like this, with a lot easier than even like say a university could have done in 20 years ago. So modern computing is kind of a big reason for this becoming kind of more into the mainstream of machine learning. Okay, one observation that we can make along these lines for the moment in terms of the interplay between computational complexity and layers and nodes. So if there are many features, which will usually correspond to having lots of nodes, then deep models with lots of hidden layers but comparatively fewer nodes per layer, I tend to kind of think of these in some sense as sort of thin. If you think about the deep neural network as running from left to right, it's going to be long left to right, but thin vertically, right? Because you're not going to have that many nodes in the at each layer. Okay, so this isn't at all a term that gets used. I'm just the way I think about them, sort of thin networks from left to right, viewed the way we've been visualizing them so far. Right? These tend to be computationally more efficient. So the alternative, what you might think is a sort of a fat network or a fat stubby network, because then you're going to have it's going to be less deep from left to right, okay, and then like kind of vertically wider, right? Another way of thinking about it, right, is that what I just described is a network that you could, if you drew the picture of it, it fits in a long thin rectangle. Whereas if you have few hidden layers and lots of nodes, that's going to be more like a square. So just kind of visual, like just thinking in very kind of broad terms. This is just what you might want is adding more hidden layers with relatively fewer nodes will increase the learning ability without increasing the computation power as much. We'll see a little bit of why when we do get to tuning neural networks next week. Okay, so then the last thing to say about the layers is the output layer. All right, and so, well, what happens at the output layer depends on the type of modeling problem. Right, so of course we have two broad categories: regression, where we want a numerical output, and classification. But then classification, there's two possibilities here. We can do binary classification, or we can do multinomial classification. Binary, where we only have two outputs; multinomial, where we have more than two, so many. Okay. All right, so regression is easy to describe. Okay, so there's a single output node. Which outputs the final predicted numerical value of the response variable. Okay, so that's it, right? So you just you're predicting a numerical value, like say the selling price of a piece of real estate for the Ames housing example, and it's simply going to output what that is. Nothing more to say there. Okay, so for classification, as already observed above, it depends on if we are doing binary or multinomial classification. Okay, so for binary, so when we're doing outputting ones and zeros or trues and falses, yeses and nos, etc. So you only need one output node, right? Because with binary output, what we're going to do is we're going to predict a probability, and then the probability of the other outcome is simply 1 minus, right? So there's one output node, and the output is a probability of a 1 or probability of a true, probability of success, however you want to describe it. Because then the probability of the other result is just 1 minus that. Now for multinomial, the number of output nodes has to equal the number of classes being predicted. Okay. And then how do the outputs work? Well, the output of the node for class K is going to be the probability that the prediction is in that class. Okay, so as an example, and one that we said was kind of implicitly in the picture that we looked at earlier. So with the MNIST data, this is, of course, a multinomial classification problem. So the output layer has 10 nodes, which for convenience we'll label Y0, Y1 through Y9. Corresponding, of course, to a prediction of a handwriting sample being the digit corresponding to the subscript on the note, 0, 1 up to 9. Okay. And so then the output of node k, for k between 0 and 9, is the probability, the predicted digit for that piece of handwriting is k. So maybe you've got some poorly drawn symbol that looks like it could be a 4 or a 9, and it predicts like there's a 45 probability of 0.45 that it's a 4, probability of 0.45 that it's a 9, and then maybe there's a 0.1 probability spread out over some of the others, like in various small like amounts. Just making something up, but that's the idea, right? So it's gonna predict the probability that a given handwriting sample is a particular digit. Maybe if you've got a very nicely drawn 0, it gives you like a probability of like 0.99 that it's a 0, and then 1 or some 1% spread out over all the others, et cetera, et cetera. So that's how the algorithm, that's how outputs would work for that kind of classification algorithm. All right, so as mentioned a couple of times, so next class on Thursday, going to be all about activation functions. So there's much more to say here, and this these sort of choice that all the possibility of choices of activation functions gives a lot of richness to the way the neural network can behave, and a lot of the flexibility comes from the choices made here. So that's what we'll discuss, and we'll see that also the choice of activation functions can vary depending on what layer we're at as well. So that second aspect of the network architecture is very important, and so we'll focus on that on Thursday.